Good morning, my dear students. So in this class I'm going to tell you about the four different methods of doing balancing. Okay, so last class I told you about the introduction about balancing and what are the different types of balancing, and what is the benefits of balancing, and what is the need of balancing in machine component. Okay, so for your syllabus we have the four different methods of doing perfect balancing. Okay, so let me start one by one. Okay, so here the process of providing the extra masses in order to countersect the effect of centrifugal forces of a first masses is known as the balancing of rotating masses. Okay, so normally if you take any one shaft, on that particular shaft there are four masses will be mounted. Okay, so that four masses should be mounted, that if you give some speed, there is a chance of rotated. Okay, so that is in some time, if you give some speed, there is a chance of producing a vibration. Okay, to make it balance one, we are going to add some extra masses on that to make it perfect balance. Okay, that is about the definition of this balancing of rotating masses. Okay, so for your syllabus they mentioned in the syllabus there are four methods of balancing of masses. The first one is a single mass rotated in a single plane, that is in a same plane, that is the first case. Second one is two masses rotating in a different plane. Let us as you take the two different masses rotated in a different plane. Okay, so that is about the second case. The third case is the several masses, that is the number of masses rotated in the same plane. Okay, that is the third case. Fourth one is several masses rotated in a different plane. So these are the four different cases you need to study. Okay, so in this class I'm going to tell you about the first case number one and case number two, that is single mass rotated in a same plane and the two masses rotated in a different plane. Okay, so let me understand first the first case. So this is based on this cases only you need to solve the problems. Okay, let us study one by one. Okay, so be serious for listen, be serious to listen this. Okay, so balancing of single rotating masses by a single mass rotating in a same plane. Okay, take the single masses that going to fixed in a some particular shaft and that will be rotated in a same plane. That is about the first case. Okay, so here I consider one particular shaft upon which a single mass is fixed mounted within some radius. Okay, so even and that is about the called as a disturbing mass. Okay, so here let m1 be the disturbing mass attached to the shaft. Okay, so I mentioned here shaft. Omega is the angular velocity of the shaft, that is in radian per second, and r1 is the radius of rotation, that is the distance of the cg of the mass m1 from the axis of the rotation of the shaft. Okay, r2 is the distance of the cg of the mass to the m2. Okay, so here I mentioned here take one particular shaft, okay, upon which a disturbing mass is fixed. Okay, so within radius of r1. Okay, to make it, if you even if you give some speed, that is angular velocity, that will be rotated with producing a effect. Okay, so here to make it balance one, there is a chance to make it balance one, we are going to put another mass, that is another direction, that is another opposite direction to make it balance one. Okay, so that is about m2 and r2. Okay, so here due to the disturbing mass m1, a centrifugal force is developed and is given by already we know that the centrifugal force is equal to m into r into omega 1 square, that is omega square. Okay, so that is in Newton. Okay, even if you rotate some speed, there is a chance of producing a centrifugal force. That force is fc1 is equal to m1 r1 into omega square, equation number 1. Okay, so a balancing of mass m2 is attached to the shaft in the same plane of rotation as that of disturbing mass m1. Okay, same what weight, that is what magnitude is there for the mass m1, same mass one we are going to fix opposite direction, that is called as balancing masses, that is m2. Okay, so for due to that the centrifugal force for fc2, that is mass 2, is equal to what, same here, fc2 is equal to m2 r2 into omega square, give equation number 2. Compare equation number 1 and 2. So you are going to get m1 r1 omega square is equal to m2 r2 omega square. Okay, that omega square both the side you are going to get cancelled. So m1 r1 m2 r1. So this is about the perfect balancing. Okay, so hence the such a balancing cases, the product of disturbing masses and the radius is must be equal to the product of balancing masses and its radius. Okay, so disturbing mass is equal to balancing masses, so r1 is equal to r2. So this is the first case about the balancing of single masses rotated in a single plane. Okay, so I hope you understand. Just to understand that, so take the consider a particular shaft here and fix to the one disturbing mass going to fixed. Okay, if you give some angular velocity, that will be rotated to make it balance one, same equal amount of mass that will be going to fix another side, so make it equal so that the given single mass is rotated in a perfect become balance one. Okay, so case 2. So similar to case 2, what here the case 2 is same. So balancing of single rotating masses by two masses rotated in a different plane. Okay, so here again case 1 will be there when the plane of the balancing masses may lie in on the same side of the plane of the disturbing masses. Okay, so when the plane is lie on the same side of the plane and of the disturbing masses. Okay, so here see the consider a particular shaft upon which a mass m is fixed. Okay, to make it balance one at the both the side we are going to fix another, that is the disturbing mass. Okay, m1 and m2, that is about the position. Okay, even if you give some angular velocity there is a chance of producing a centrifugal force that is equal to fc1 is equal to m1 r1 into omega square. That is about the position of the plane. If you come to the diagram angular position of the masses, okay, so here the one mass m, that is the mass m is a fixed mass, that is with a radius of rotation of r1. If you give some angular velocity to make it balance one up on the same side, we are going to fixing the balance, that is disturbing masses m2 and m1 with a different radius of rotation, that is called m1 and m2. Okay, so the first figure shows the position of the plane, that is with a mentioning length, and the second diagram we are going to tell you about that shows about the angular position. Okay, next let us resolve these cases. Okay, consider a disturbing mass m lying in a plane A to be balanced by two rotating masses m1 and m2. Okay, so in the question only they mentioned that a single plane rotating in two planes. Okay, so m1 and m2 we are going to adding, that is we are going to fixing to make it balance one. Okay, lying in a two different plane L and m as shown. Okay, let us assume that r1 is the radius of rotation of mass m1, r2 is nothing but radius of rotation of mass m2, r is the radius of rotation of m plane. Okay, so similarly length distance between the a and l, l2 is nothing but distance between the a and m, and normal l is distance between the l and m. Okay, so after looking diagram only you are going to what this you are going to get this. Okay, next one is therefore the centrifugal force created, that is exerted by a mass m is equal to in the plane a is equal to fc is equal to mr omega square. Okay, so this is the due to the plane a. Similarly centrifugal force exerted by a mass m1 is equal to in a plane l is make it 1. Okay, so that is fc1 is equal to m1 r1 omega square. Okay, so similarly fc is exerted by a mass m2 in a plane m is fc2 is equal to m2 r2 omega square. Okay, since the net force acting on that particular shaft is must equal to 0 because this is about the D'Alembert principle, we know that. Okay, so fc is equal to total centrifugal force is equal to the attaching mass, that is the disturbing mass fc1 plus fc2. Okay, substitute their formula, you are going to get what mass into radius. Okay, that omega square get going to cancel. So remaining is mr, that is mass into radius is equal to m1 r1 plus m2 r2. Give equation number 1. In order to find the magnitude of balancing the forces in the plane L, that is a dynamic force that will be created in the in the shaft taking the moment about p. Okay, so moment is equal to what? Force into distance. Okay, moment is equal to what? Force in mass into perpendicular distance. Okay, therefore fc1 into L, that is the moment is equal to fc centrifugal force into that is the distance is equal to what? L2. Okay, substitute the formula, that is the fc1 fc2, that is fc, you are going to get omega square we're going to get cancel. So remaining is m1 r1 L is equal to mr into L2. Give equation number 2. Okay, like that similarly take the moment about the theta. Okay, so with respect to 2, okay, fc2 is equal to L and fc is equal to L1. Okay, substitute their formulas. Okay, again you are going to get omega square get going to get cancel. So remaining is m2 r2L is equal to mr L1. Okay, so when this is about the first case. Okay, second case if you come this we are going to that is second case is what? When the plane of the balancing masses lies on the one end of the plane of the balancing masses. Okay, just to take the reverse of that. Okay, even if you make it two unbalanced masses here, left hand side right hand side, to make it balance one if you keep the center one. Okay, additional masses. Okay, so that I shown you here. Again figure A shows the position, figure B shows what? Angular position diagram. Okay, so in this case also same procedure you are going to follow here. So in this case the mass m lies in the plane A and the balancing of masses lie in the plane L and m. Okay, so this is in between the plane L and m, you are going to make a balancing m, we are going to fix that. Okay, so here fc is plus fc2 is equal to fc1. Okay, just to observe the equation here, previous case is different, here is different. Okay, so that m1 r1, just to substitute the formulas, mr omega square that is L plus m2 r2 omega square is equal to m1 r1 omega square. Okay, omega square going to get cancelled. Therefore m1 r1 is equal to mr plus mr2 r2. Give equation number 1. Again take the moment about the p, same what we applied in the previous case. So summation of moment is equal to 0, that is fc1l minus fcl2. Okay, so here again if you substitute their formula, you are going to get m1 r1 is equal to mrl2 divided by l. So give equation number 2. Okay, again take the moment about theta. So from the equation, moment is equal to what's force into distance, fc2 into l, that is fcl1. Okay, again you substitute the here formula, m2 r2 omega square l is equal to mr omega square l1. Okay, so m2 r2 going to, so if you again solve that problem, that is that equation, you are going to get m2 r2 is equal to mr l1 divided by l. Give question number 3. Okay, so this is about what the final equation of this second case, that is what the when the balancing masses lies on the one end of the plane of the balancing of masses. Okay, so this is about just to understand that how we are going to make it balance one. Okay, in the first case, when the plane of the balancing masses may lie on the same side of the plane of the disturbing mass. Okay, this is about the first case. Second case is the opposite of that. So this is about the first and second case. Okay, I hope you understand these two cases. Okay, again second slide we are going to tell you about the third and fourth cases. Okay, so how we are going to make the different types of masses to make it balance one. Okay, that is about the main things to study about this. Okay, so I hope you understand this. Thank you.